Hello, everyone. We are going to continue our exploration into solution chemistry in Module 7. And we are going to start this lecture with talking about the dilution of a solution. So solution dilutions. All right, let me start sharing my iPad. Okay. Many times when you use a solution in the lab, you have a solution that might have a specific molarity. Like, let's say your lab calls for 1.5 molar HCl or 0.5 molar HCl or maybe 3 molar HCl. Well, it would be pretty inefficient to have all of those infinitely possible concentrations sort of prepared and bought from a chemical stockroom and sitting in your shelves all year. So basically, when chemists use a solution in a lab, what they've done is they've prepared that solution according to what is necessary to use in the lab. So what you actually purchase from a chemical supply house is a stock solution, which is something that is concentrated. So it usually has a fairly high molarity. And then I use that to prepare solutions of lower concentration by diluting that stock solution. So dilution is the process of lowering the concentration of a particular solution by adding more solvent. If I add more solvent, my volume of the solution increases. The amount of the solute doesn't increase. I'm only adding solvent. I'm not adding any more solute. So the volume gets larger, which means the concentration gets lower. So when you dilute a solution, this is a key important fact. The number of moles in the solution does not change. Only the volume changes. The moles you start with initially equals the moles in the diluted solution. So the moles initially equal the moles diluted. Now remember, the number of moles is equal to the volume in liters times the molarity in moles per liter. So I can write this expression, which says the volume initial times the molarity initial is equal to the volume diluted times the molarity diluted. A lot of times you'll see this written as M1V1 equals M2V2, and this will be referred to as the dilution formula or the dilution equation. To do this, I'm going to use a technique similar to that I used when I was actually preparing a solution. I have the volume to be diluted is drawn up into a pipette and then delivered into a volumetric flask. Solvent is added to the level just below the calibration mark and the flask is shaken. And then I'm going to add right to that calibration mark because I know when I use a volumetric flask that this is going to be 100.0 something, plus or minus usually 0.01 milliliter. So again, I use these volumetric flasks specifically for making precise and accurate solutions. Here's an example. Sulfuric acid, which is H2SO4, is normally purchased at a concentration of 18.0 molar. So what I want to do is prepare 250 milliliters of a solution that I want to be 0.500 molar. So here's my initial, here's my final. So my molarity initial times my volume initial is equal to my molarity final times my volume final. If I want to calculate this, I'm going to dissolve by molarity initial, which gives me this equation here. So now I pull it in, I put the values in. So this is my final molarity, this is my initial molarity, and this is the final volume that I want. So this tells me I'm going to add 6.94 milliliters of my stock solution, that solution that was 18.0 molar, and in a 250 milliliter volumetric flask. And then I'm going to dilute to that line in my volumetric flask. And at that point, what I'll have is 250 milliliters of a 0.500 molar solution. So here's a practice problem. Hydrochloric acid is obtained in 12 molar stock solutions. So this is HCl. What volume of stock solution is required to make 500 milliliters of a 0.145 molar dilute solution? So this is very, very similar to the problem that we just talked about. If I look at my initial concentrations, this would be the stock solution. I have my molarity is 12.0 molar. My volume is what I'm trying to find. I know my final concentration, my molarity is going to be 0.145 molar or moles per liter, and my final volume I want is 500.0 milliliters. So again, M initial times V initial equals M final times V final. I'm going to isolate V initial just like I did before. And what I get is M final times V final over M initial, which is equal to M final 0.145 moles per liter, or molarity, times V final, which is 500.0 milliliters. And then my molarity initial is 12.0 molar. Notice the molar cancels and I'm left with milliliter. You should also notice that I didn't convert to liters in this particular example. And that's because since this is more or less a ratio, it doesn't matter what unit my volume is in. So I have 0.145 times 500 divided by 12.0, and what I get is 6.04 milliliters. So again, this is the amount of HCl. So I'm going to take 6.04 milliliters of my 12 molar HCl. I'm going to add to a volumetric flask that is 500 milliliters. And then I'm going to dilute that 6.04 mils of that concentrated HCl with water. And then I am going to have 500 mils of my 0.145 molar solution. Here is another example of a solution dilution. And this takes a little bit more time. What I have is 11 grams of glucose. So I have 11 grams of glucose. And I know that's C6H12O6. I am in a volumetric flask and I add enough water to dissolve the glucose by swirling. And my solution volume here in that volumetric flask is 100.0 milliliters. And then my flask was shaken. So that's my solution 1. Then I take 20.0 milliliters of solution 1 and dilute it to 0.500 liters. What I want to know is how many grams of glucose are in 100 mils of the final solution. Okay, I'm going to get a new note so I can do this. And let's reiterate what we have. I have a volumetric flask, which is 100 milliliters. I have 11.0 grams of C6H12O6. And this is going to be my solution 1. So let's calculate the molarity of this solution number 1. If I have 11.0 grams of C6H12O6, I need to calculate the moles. So I need the molar mass of this compound. So I'm going to take 12, actually not that, I'm going to take 6 times 12.011. And then I'm going to add that to 12 times 1.008. And then I'm going to add that to 6 times 16. And my whole molar mass of glucose is now 180.162 grams of C6H12O6. When I look at that, I find I have 0.061056 moles of C6H12O6. So the molarity of this solution 1 is going to be equal to the moles of glucose over the volume of the solution, which is equal to 0.610, 0.0, don't drop your zeros, that'll be the kiss of death, 0.061056 moles all over 0.100 liters, because 100.0 milliliters is equal to 0.1000 liters. When I do that, I come up with a molarity of I'm gonna do 61056 moles per liter, or molarity. Now, I have 3 sig figs there. I have more than 3 sig figs there. So remember, my significance is to that 0. So that's 3 sig figs. Remember, this is going to be 3 sig figs. Now, the second part is I take a volume of solution 1, which is equal to 20.0 milliliters. And I'm going to dilute that until I have 0.500 liters. So this is a dilution. My initial is molarity of solution 1 is equal to 0.61056. My volume of that initial solution is 20.0 milliliters, or I need to have these in the same unit. I can't use milliliters and liters. I either have to use milliliters and milliliters or liters and liters. So I'm going to convert this to liters. This is 0.0200 liters. My final is going to be unknown until I do this dilution calculation. And then my volume of that final solution is going to be 0.500 liters. So if I use M1, M initial, V initial is equal to M final, V final, I'm looking for M final. So to solve that, or this is final, this is going to cancel, and what I get is the molarity of this second solution is the molarity of the initial solution times the volume of the initial solution divided by the volume of the final solution. So what I have is 0.61056 molar times 0.0200 liters divided by 0.500 liters. That cancels. And what I get is my molarity times 0.02 divided by 0.5, and I get a molarity of 0.02442246. And I'm going to go to 3 sig figs with that as well. Now that's not the answer, because it says how many grams of glucose, which is my C6H12O6, do I have in 100 milliliters of this final solution. So now, remember, my number of moles is equal to the molarity times the volume in liters. So I can calculate the moles of glucose by using this equation. So this is going to be 0.0244 molar times 0.100 liters, and I'm going to get moles. And that gives me 0.002442224. Remember, I'm significant to there. Moles of C6H12O6. So now that I have the moles of my glucose, I can go ahead and convert that to grams because I know the molar mass now. For every 1 mole of C6H12O6, I have 180, let's look up here, 180.162 grams of C6H12O6. Moles will cancel, I'm left with grams. My final answer then is 0.00244 times 180.162, and I get 0.440 to 3 significant figures, grams of glucose. This is my final answer. So that is the answer to this problem. And the next topic we're going to do is solution stoichiometry. But we're going to stop here with the dilutions and then come back and revisit solution stoichiometry in just a little bit. So I will see you guys soon in order to talk about solution stoichiometry and continue our discussion of Module 7.